All right, as for today, we're going to look at regression. This is our last big topic that we're investigating. And we already looked at a little bit of this last time with correlation and scatter plots. And this is an extension of that material. So we have quantitative versus quantitative data. And remember the question I asked there to identify, is it quantitative? Does it make sense to take an average of this? So we're going to jump right into an example here. The Great Plains Railroad is interested in studying how fuel consumption is related to the number of rail cars for its trains on a certain route between Oklahoma and Omaha. A random sample of 10 trains on this route has yielded the data in the table below. Data is then in StatCrunch, rail car versus fuel. So the very first question to ask, and this is the extension of what we were doing last time, describe the relationship between the number of rail cars and the fuel consumption of a train. In order to do that, we need to make our new picture, all right? Our new picture, whenever it says describe the relationship or association, our new picture is a scatter plot. When describing the relationship, aka describing scatter plot, we identify three things: direction, form, and unusual features. And so those are the three things, all right, that we are going to identify. So to StatCrunch we go. And this is the rail car versus fuel data set. And again, I know this is quantitative data because when I look at this, all right, even though these are all whole numbers, when you have a bunch of them, all right, that means, okay, and especially when I have two variables connected, all right, most likely this is quantitative data. Also, I ask myself the question, can I have an average number of rail cars attached to a train? Yeah. Can you have an average fuel consumption? Yeah, that's exactly what miles per gallon is, right? It's calculating your average miles per gallon of gas used. So our new picture, graph, scatter plot. And then which one is X, which one is Y? All right, our X variable, we ask the question, which one comes first? All right, do you attach the rail cars to the train or do you find out your gas mileage first?
The first one, maybe.
Yeah, we attach, it's just like when you build a car, they determine the weight of a car first, all right? We determine how much the car weighs, and then we figure out the gas mileage, right? And that's the same exact principle here. Number of rail cars is my X, and I want to predict the fuel consumption used by that. And so we create our scatter plot, our new picture, and this is our go-to picture for regression. So with this picture, then we need to identify direction, form, and unusual features. So the direction, as I trace from left to right, it is positive. The graph is going up. All right, the form, all right, we have several options, but the main one we want to look for is linear and non-linear. And this looks like a line. So I'm going to say that's linear. And the last one is unusual features. Any points or set of points that don't fully match the general pattern. And in this case, I would say none. It looks like pretty much all the points follow this general pattern the same. So my direction is positive. Form is linear. And no unusual features. And so describing the relationship is really pretty simple, all right? It's about making sure that we include those three important points. The linear model, all right, is about fitting a line to the data set, all right, a line that we're actually going to be familiar with. Before we get to that line that we're going to fit to the data set, we have to talk about the stat version of this, because a line is, when we discuss this, it's going to be something you're familiar with. But in order to do a best fit line, which is what we're doing, we have to talk about the errors, and we call those errors residuals. A residual is the observed value minus the predicted value. All right, the actual number versus our guess of that number. Now, the good news is StatCrunch is going to do all these calculations for us, creating the best fit line to that data. But, all right, I want to talk about what StatCrunch is doing while it does that. So this distance, these black lines, okay, so this blue line is our predicted line. These vertical black lines, all right, those are the residuals. That is the distance, all right, from the actual value to the predicted value. And some will be positive and some will be negative. StatCrunch goes through, all right, and I mean, Excel does this. All computer programs do this. They iterate a ton of these lines until they find the best fit line. And that best fit line, all right, is the minimum value of all those residuals. All right. So it goes through and calculates how to make all these vertical black lines, all these residuals, the smallest they can be. And that's a really nice process. And then it fits a line to the data set. The equation of a line you should be familiar with. All right. Y equals mx plus b. All right. All that algebra that you learned, all right, here's where it's finally useful. Now notice that StatCrunch, and it writes it like this: fuel consumption equals the intercept, the b value, plus the slope times num rail cars. So it puts it into context. All right, so it's not using x's and y's, it's actually going to use the context of your problem. But that equation is an equation that we're very, very familiar with. Y equals mx plus b. I mean, you learned that 10 plus years ago. All right. This concept then, all right, is what StatCrunch does in order to find our best fit line. And then just as a note, a negative residual means the value is too big. That's an overestimate. All right. So that would be where the red dot is below the blue line. And an underestimate is when the blue line, all right, is below the red dot. And those result in positive and negative residuals. The other nice thing, all right, that StatCrunch does is that the errors will be normally distributed. And the errors are those distances off the line. The errors end up being normally distributed. Meaning that best fit line, right, within 1 standard deviation, it catches 68% of our data. Within 2 standard deviations, it catches 95% of our data. And within 3 standard deviations, it catches 99.7% of our data, the 68, 95, 99, 7 rule. And so that's another really nice property. All right, so it's all these same things that we have been doing, all right, they keep coming back. It's just fitting a new type of problem to same concepts that we've already learned. So now to our line specifically. So like I said, our line is y equals mx plus b. That's the general equation of a line. Now in StatCrunch, we write it ever so slightly differently, but those values still mean the same thing. All right, y hat, that's our y, equals b0, that's our intercept, plus b1, that's our slope, x. Now the official equation of the line is y equals beta 0 plus beta 1 x plus epsilon. Now, I want to talk about, I'm going to do a proof. And when I say proof, it's really just a justification, because the interpretation is what's actually going to matter here. So feel free to pay attention or ignore me until the very end. But if I take my initial line, and I'm going to take an expected value of this line. An expected value is just a fancy way of saying an average. Expected values can go across all mathematical operations. And so, like I said, an expected value is just an average. So I can actually rewrite this first term as y bar. The average of a constant is just a constant. And then, as we saw above here, the errors are normally distributed, unimodal and symmetric, all right, and have a mean of 0. Which means the expected value of x is x bar, and then the expected value of the errors, we would call that e bar or epsilon bar. And since, all right, that is 0, that means that that value goes away. And I'm left with the average, all right, y bar plus beta 0 plus beta 1 equals x times x bar. So I end up with averages related by these constants. Well, with all constants, aka parameters, we've had lots of parameters. P, mu, sigma, all right? The true proportion, the true mean, the true standard deviation, all right? We've gone through all of these. Well, now I'm just going to add some more. Beta 0, the true intercept, and beta 1, the true slope. We estimate those population parameters with sample statistics. For P, we estimate it with P hat. With mu, x bar, sigma, with S, and now our new notation. Beta 0, we will estimate with B0. And beta 1, we will estimate with B1. So we initially did an expected value. We got it down to an equation with parameters. Then I'm going to estimate those parameters with sample statistics. And so This is the form of our regression line. And I did all that justification just to say these two words. Well, three words. We knew it was a line before. So the two words are estimated expected. And I only did that justification because when we start interpreting, those two words are what we need to make sure we have in our interpretation. Because this regression line is an estimated expected line. Basically, we are guessing on average what is happening. So when we interpret, we need to make sure that we include those two words in our interpretation, and we will see an example of that. But I did that whole proof justification, just to pay attention to those two words. Okay, and so, like I said, the model, and again, y equals mx plus b is something that you have been doing all along. We have a slope, we have an intercept. StatCrunch is going to calculate those values for us. Even though you have been doing this algebra for a very long time, what you probably are unfamiliar with is the same thing you're unfamiliar with of everything in this class: interpretation, right? And that's what we're going to focus on. The calculation is nothing, right? StatCrunch is going to handle it. It's going to spit out that line. Then we have to interpret what that means. But one big thing that we are going to do is we're going to remember, like, what y equals mx plus b, and specifically, what is the slope? As a note, the slope breaks down, all right? And you may remember this, the rise over the run. When you were calculating the slope way back when, all right, you calculated it as the rise over the run, the difference in y divided by the difference in x. And that's going to be important for our interpretation. Before it was all about, oh, find the equation of a line. Well, computers do that better. What computers don't do is interpret, and that's what we're going to focus on. Also notice one more thing. So in these calculations that StatCrunch is going to handle, notice what's here, R. That's what we just talked about. In order to calculate the slope, you actually involve the coefficient of correlation. And that's the natural transition. Scatter plots to coefficient of correlation to regression. If you fail your conditions for correlation, you stop, which means you do not proceed to regression. All right, so those conditions are important. And so furthermore, yes, regression and correlation are closely related. So our same conditions that we had in correlation that we were talking about last time, all right, we are going to continue to discuss this time. We check all three of those conditions, all right, to make sure that they are satisfied so we can proceed to regression. All right, so back to our rail car example. We want to estimate the fuel consumption associated with the number of rail cars, calculate the coefficient of correlation, and determine if it is useful, which means we need to check our conditions. And so we have three conditions, quantitative variables. So this one is, again, just about asking ourselves. All right, and we already kind of checked this when we were creating our scatter plot. Can you have an average fuel consumption and it makes sense? Yes. All right, can I have an average number of rail cars attached to the train and does it make sense? Yes. All right, so those ones, you really just kind of check them in your head. All right, does it make sense? All right, there's no like number to compare to like success, failure, or large enough condition. Okay, those are just ones you have to think about identifying if it's quantitative data or if it's categorical data. And that's a big deal. All right. But we got to make sure we check those conditions. The straight enough condition, that always comes back to, all right, our definitions of the scatter plot. How did you define your scatter plot? Oh, we defined the form as linear. That means the straight enough condition is met. If you defined it as exponential, parabolic, none, circular, curvilinear, anything else, then that condition fails. And the no outliers condition, that comes back to basically the unusual features. So two of those refer back to basically something you likely did when you first started the question. All right. Because the first thing you should do is look at a picture. All right. Look at a picture, and this is our new picture. All right. Unusual features. Well, no, I don't think we have any outliers because we defined no unusual features. So both of those go back to how you describe the initial association. Form defined as linear, check. No unusual features noted, check. All right, so the conditions are met. And so R, which I'll calculate in just 2 seconds here, is useful. All right. And all of this now is about R is useful or R is not useful. All right. So it's not we're fitting a distribution anymore. It's just R is helpful, R is not helpful. All right. And the calculation. So that was stat, summary stats, and correlation right there. Select your two variables and hit compute. All right, so 0.9836, 9836. Okay, the regression output, which we're going to look at in just 2 seconds. But the thing is there is a ton of output here and a lot of graphs that we get as well. The biggest thing, all right, the biggest things to note is R squared, all right, because R squared is our coefficient of correlation squared. Now, if you recall, when we interpret the coefficient of correlation, we say that, oh, variable X and variable Y are correlated with a value of, 98. So the interpretation is not great. So we actually interpret R squared because that one has a much better interpretation because that's actually a variance. And interpreting a variance has a better interpretation than basically that was essentially a standard deviation before. And sometimes a standard deviation has kind of a weird interpretation, but we like to interpret R squared and we're going to go through that one. The other big thing to note is the estimate of the standard error actually comes down to this analysis of variance table and the value associated, what's known as the mean squared error. This is how much variation is left over after we fit our line. And so ideally we want that value to be small, but small is relative. And so that being able to calculate those two values is kind of important. StatCrunch gives us a lot of info, but those two, we need to understand the relationship because it helps with our interpretation. Okay, so our num rail card data. Stat, gonna undo that. And guess which one we go to? What topic are we in? Regression. All right, and this is the last of it. So we're only going to do simple linear regression in here. We already picked our x and y variables when we made our scatter plot. And so some good news, don't need to mess with that, don't need to mess with that. All right, we will occasionally use prediction of y, but the big one is, all right, we want the fitted line, and then we're going to do histogram of residuals, QQ of residuals, and residual versus x value. All right, so these are all about our conditions as well. But two of these, I mean, histogram and QQ plot, we always do that, right? Okay, so let's take a look at the output. So it says, what was your dependent variable? What was your independent variable? That is, which one was your y dependent? Which one was your x? All right, so it reinforces that. Then the next thing it gives you is it gives you the equation of your line. All right, y equals mx plus b, written slightly differently, but that's the equation of a line. And boom, it gives it to you. Also, it tells you your sample size. It calculates the value of r and r squared. And again, this is about interpretation. And this is that estimate of standard error I was talking about, 4.36. That value is the square root of that value. So all these values up here are actually written right here as well. Notice, sample size is 10. It says total degrees of freedom is 9. Remember, degrees of freedom is n minus 1. Right? That was one of the things we learned when we first started doing means. 10 minus 1 is 9. So all this information up here is also repeated down here, so it's reinforcing what you know. Also notice right here, parameter estimates. 10.68, 10.68. That value is right here. Slope, 2.15, 2.15. So it has those values here as well. It then runs hypothesis tests on those values. We're going to talk about that more in a minute as well. We're going to break this analysis down when we interpret it, but there's a ton of info right here. Okay. Also, right, sum of squares model plus sum of squares error makes the sum of squares total here. 4511 plus 152 makes 4663. All right. So these values are additive here. So there's a lot of good info here. All right, and we'll go through those graphs one at a time as well. Okay, so let's start breaking that info down one piece at a time. Hypotheses. Okay, so the good news, finally, our hypotheses for regression never change. They are literally always HO beta 1 equals 0 and not equal to. No greater than, no less than, no anything else. Okay? We only test these hypotheses because, all right, think about what this is saying. Beta 1 is the slope. If the slope of a line is 0, what kind of line do you have? So if the slope of a line is 0, what kind of line do you have? A horizontal line. You're exactly correct. All right. So that's saying the line is horizontal, and if the slope of the line is not horizontal, then either your line is that, or that. All right. So your alternative hypothesis is saying that you either have a slanted line, or your null hypothesis says you have a horizontal line. And that means that there's either a relationship between X or there is not. And so that's why we don't need to ever change our hypotheses, because these equations actually relate to what a line looks like. All right, so the overall test. So the overall test uses the F statistic. So in our case, there's only one spot that says F statistic. That's right here. So that uses, the overall test uses the output from the analysis of variance table, 237.18, and a p-value of 0. And again, all that's going to be given. The F statistic is a new test statistic, but the F statistic is going to be one that we're actually kind of familiar with. All right, we're going to talk about that in just 2 seconds. So 237.18. And a p-value of 0. And it says it right here. The F statistic is just the square of the T statistic, all right? And so the T statistic for the slope, all right? We're going to have multiple T stats here. Got to make sure we pick the right one. All right, so with a p-value of 0, reject or fail to reject HO.
Let's see.
Got your rule?
Fail to reject or what?
Reject. So we reject HO at a 5% significance level, all right, or any significance level, because the p-value is 0. And now our interpretation is going to be slightly different. There. So, I mean, it's going to start the same. There is strong evidence to show. Okay. So now, though, we're talking about the relationship between X and Y. So we're not talking anymore about, oh, this mean is bigger than that mean, all right? Or that mean is bigger than 5, okay? It's actually about the relationship between X and Y. And so all of this is about putting it into context as well. So we have number of rail cars is our X variable, and fuel consumption, all right, as our Y variable, and of a train for both of them. So there is strong evidence to show that the number of rail cars on a train is an important predictor of the fuel consumption of a train. So our interpretation now is about how our variables X and Y relate to each other, because that was the whole point. All right, this hypothesis test says that if you end up with a horizontal line, there is no relationship. Regardless of the number of rail cars, then that doesn't affect the fuel consumption. Logically, we know that not to be true, and that's why we rejected HO and we say there is a relationship. The coefficient test, notice the hypotheses, all right, are exactly the same. And that's because, all right, for simple linear regression, the overall test and the coefficient test are the same test. Now, I point this out because that's only true for simple linear regression. Now, good news for us, that's all we're covering. So once you identify one, you should know the interpretation of the other. The difference lies in what test statistic we use. For the coefficient test, that uses the t statistic. And which t statistic? It uses the t statistic, all right, for our slope data. So it uses the one that is associated with slope, this 15.4, and a p-value of 0. Notice these p-values will still be the same. So, reject HO at a 5% significance level. There is strong evidence to show that the number of rental cars on a train is an important predictor of the fuel consumption of a train. That should look familiar. It's literally the exact interpretation we just did above. All right. And that is my point. The coefficient test and overall test are almost exactly the same. The only difference between them is one uses the F statistic and one uses the T statistic. But as I just said, the F statistic is the T statistic squared. That means that 237.18 equals 15.4 squared. Those were our two test statistics. There's 15.4. There's the 237.18. So that relationship indicates that yes, all right, they are mathematically the same test. All right. So basically, if you do one, and I wrote it out there just to emphasize they are the same. But most of the time, I just say ditto. All right. It is the same because once you did one, all right, you can do the other. The only thing you want to make sure you can identify is the terminology there. If it says do the overall test, make sure you grab the F statistic. If you're doing the coefficient test, make sure you grab the T statistic. The conclusion, the p-value, the hypotheses, those will all be identical. The only difference is the test statistic used. All right, on another note, the coefficient, we tend not to test that because that really just, it usually doesn't have good interpretation. And what matters most is the relationship between X and Y, not where it crosses the Y axis, right? That's what the Y-intercept means. It's where it crosses the Y axis, right? The interpretation is not very meaningful, and we're going to talk about that in a little bit. So those are the only hypotheses we do in regression. And they are the same hypotheses, and they never change. So along those lines, what else we do? Well, we only have one hypothesis test, but what we do is we interpret a lot of our pieces of our regression model. Remember what the slope is. The slope is the rise over the run. You run some distance, right? Travel some distance on X, and then rise a certain distance in order to get the slope of a line. That's how you calculate the slope. Well, the good news is our interpretation is very similar to that. As X increases by 1 unit, right? So as I run 1 unit, Y increases, notice, by an estimated expected, right? That was that proof we did, right? Because that interpretation needs to be here, all right? X increases by an estimated expected rise number of units, and that is what our slope is. So there's the generic interpretation. Okay, so for our case, X was our number of rail cars. Okay, so as I increase the number of rail cars by 1, okay, so let's put that into slightly better English. For each additional rail car I add to the train, right? So for each additional rail car added to the train, Y hat, our Y variable, the fuel consumption of the train increases. Now be aware that I say increases here, but if the slope is a negative value, it would be decreases. All right, so you can always say increases by a negative, but it's super awkward. Just make sure you change that to decreases if that value is ever negative. But in this case, my slope is positive. The fuel consumption of the train increases. By an estimated expected B1 units. Now here's the other good part. That means I just find the slope. What's the value of the slope?
Estimate.
Huh?
Estimate.
Yeah, it's just the first one, right? It's the one, and it literally says there's the slope. It's 2.15. All right. So, all right, it's all in the output there. Now it's also that value's up here, but I think it's even more obvious that it's right there, right? So, all right, for each rail car added to the train, the fuel consumption increases by an estimated expected 2.15. All right, then units, and in this case, it says up here at this very start of the problem. All right, fuel logs per mile, right? And sometimes X has units, but the units of the number of rail cars is 20 rail cars, right? 31 rail cars. This is actually, right, 58 fuel logs per mile, 52 fuel logs per mile. And so again, that's just interpreting, all right? This is y equals mx plus b. Something you have done over and over and over again. But what you probably haven't done is fully interpreted what that means. The actual only stat part that we added were these two words, estimated, expected. The rest of this, you could have done already, all right? So this is stuff that you definitely should be familiar with. All right, similarly, I want to interpret the intercept, the y-intercept, and the general interpretation at x equals 0, the estimated expected y hat is the y-intercept units. So again, the general interpretation is exactly what you think it is, because the general interpretation is basically saying, where does the line cross y and what does that mean? All right, this is the y-axis, and what does that mean? So at x equals 0, all right, so for our case, when there are no rail cars added on a train, when there are no rail cars on a train, okay, that means a train consists of engines only, all right? So the estimated expected is, and then again to our output, intercept 10.68. Now, for the intercept, we often include a meaningfulness attachment, all right? And especially, we have to make sure this makes sense. And when it doesn't make sense, we definitely want to explain this. Now, the good news for us, this one actually seems to make sense, all right? When a train is only engines, does it still burn fuel? Yeah, right? The engine takes power to move. So just the engine burns fuel on its own, all right? A lot of times, like if this value was negative, right? Well, there's no way a train doesn't burn fuel, let alone negative fuel. Hence, the train is actually producing fuel, all right? Which doesn't make sense. And so a lot of times we say, this is not meaningful because we can't have negative fuel or negative fuel burn, something to that nature. All right, we're going to see one of those, but this one is fun. I was like, logically, that totally makes sense. All right, so regression has two real strengths: interpretability and prediction. So prediction has come in a lot of forms now. And I mean, especially with AI coming along and neural nets and things like that, you put in an input and get out an output. But the strength of regression is that the interpretability is tangible, all right? And it's so easy to calculate, and StatCrunch does this for us as well. So I have my equation, my y equals mx plus b equation here. Right, I have my equation y equals mx plus b. And basically, given any x value, I can predict a y value. Similarly, given a y value, I could predict an x value. StatCrunch will do this for us as well. So I wrote up my equations here generally, and notice I even wrote 10.66 because StatCrunch is going to handle it. I want to predict the fuel consumption for a train that has 35 rail cars. Well, the calculation that is happening is I'm putting in 35 for x, multiplying it by the slope, adding it to that value, and I get out the value. All right, similarly, I want to do that for 40. Now, watch StatCrunch do it. And so we know, go back into options, edit. And this is where we use prediction of Y. So this is the only other thing we do in here. And it says put in an X value. So I'm going to put in the value 35, and I can predict multiple values at a time, comma, I'm also going to put in the value 40. And it's going to calculate these two values for me. And it gives it in the output down here. For the value X equals 35, prediction of Y, 85.91, 40, 96.66. And notice, those are the values we had here, 85.91, 96.66. So StatCrunch will calculate those values very, very fast. Now be aware, that only works when I input the X value and spit out the Y. If I want the Y value, if I want the X value given a Y value, I do need to do a little bit of algebra to solve this, but it's not hard. All right. And so it's very, very nice for prediction as well. And I can predict just tons and tons of values, all right, with using regression and using StatCrunch. All right. The other big thing. Okay, so we interpreted the slope. We interpreted the y-intercept. The other big thing we interpret is r squared. And those are the three big interpretations we do. The slope and the intercept, those are averages, all right? So we predict averages. The r squared, that is a spread. And that's basically the first thing we talked about in this course is center and spread. And here we are at the end of the course, and we're still talking about center and spread, just like we are still talking about categorical and quantitative data. And that's what stats breaks down to. Stats has details. Yes, it can get complicated, but the big concepts, they are the same. And the point is to not get lost in the details. Big concepts, that is how you run through all data. All right. It looks complicated when you get into nitty-gritty stuff, but overall, very simple, big facts that we deal with. Okay, so r squared is the amount of variation accounted for by the model divided by the variation divided by the total. And that's what I had with that formula. And that's because I wanted to point out that formula, and I want you to understand that formula because it helps you with the interpretation. So for our case, all right, we have an r squared value, which is given right here, 96.74, 96.74. Okay, so approximately 96.74% of the variation So approximately 96.74% of the variation in the fuel consumption of a train can be explained by the variation in the number of rail cars on a train, all right, using the simple linear regression. Now notice the important word on this one, variation. All right, the important words, all right, in our interpretation of slope and intercept. Estimated, expected, all right? We need to make sure that we have those words, all right? Estimated, expected, when we interpret the slope and the intercept, and we need the words variation or variability or variance, a V word there, all right? In the interpretation for R squared, all right? Because that's what it is, has to represent center and spread. Estimated, expected, that means it's an average. Variation, that means it's a spread. All right. Okay. So assumptions and conditions. All right. So notice that we had our initial conditions correlation before in order to get into regression. If those fail, we can't do regression. But regression has its own conditions on top of that. Residuals. All right, all based on residuals, looking for things like nonlinear pattern, all right, and some other things. So our residuals, observed minus predicted. It's a very simple concept to calculate, all right? And even when we did that prediction, all right, and StatCrunch, I mean, you could calculate these values by hand, the actual value minus the predicted value, the guess value, all right? But StatCrunch does these calculations for us and then plots these values. The biggest plot that we're going to look at, as always, is the histogram. Because the residuals had a big assumption on them. It said the residuals were normally distributed. Now, important, not the data. The data is not normally distributed. It is the residuals that are normally distributed. So, all right. And all this output, all right, so we've still just been looking at the first page. The second page is a scatter plot. Oh, so here's the big thing. When you go into regression, you can actually skip doing the scatter plot, like doing it individually by going graph scatter plot. You can also skip going to correlation, because if you go directly into regression, it gives you the scatter plot, it gives you the correlation, and it gives you all the regression output. So I don't do those other two pieces. I go directly here. And here's the other nice thing about regression that a scatter plot doesn't have. Initially, one of the big things that people struggle with when the data is more complicated than this, they struggle to see, we kind of saw it in the tree height versus diameter data set. It was like, gosh, is this going up or is this going down? I can't even tell. What does this one give us? It puts a line in the data. So you actually see, is this positive? Yeah, why? Because the line goes up. So the more complicated the data is, the more helpful that line is. Because even I struggle sometimes when it's like, gosh, is it like that? Or like I can't, when it really gets like close, all right? And so that line is super helpful to help me describe the association. Okay, so that's the first plot. The second plot is this histogram that we're going to look at. And right, with a histogram, unimodal and symmetric. We want the same thing as always. Is this unimodal symmetric? No. I'm even pretty like lax on describing it. But finally, I'm going to say that's unimodal left skewed. So that condition fails. Now, good news. This is an OR condition. All right. Our next graph we always go to is the QQ plot. On the QQ plot, remember, we want our values falling approximately near the line. Now, I'll admit this one doesn't look great, but that's close enough. All right. We need a pretty extreme pattern. And if the values fall approximately on the line, then that's all we're looking for. Okay, so the histogram or the QQ plot, it is an OR condition. And so then I can actually say, all right, the conditions are met, or actually even more specific, at least one of the conditions is met. So at least one of the conditions is met. We can assume the residuals are normally distributed. And that is our assumption there. If both of those things look very, very bad, then the condition fails. This one is a new one. So that's a familiar one. Histograms, QQ plots, that's stuff we've done repeatedly. The residual versus X value plot. And this is to make sure that we actually got all the variation out of the data that was that we were supposed to get. And this is our third graph in our regression output. With this plot, what I'm looking for here is a flurry of points. No pattern, no distinct shape, nothing that I can connect all these points with. Okay? If it looks like a random scattering of points, that's actually the best thing that can happen. Because that means that my line, actually, the data is linear. If it is any other shape, that means the data is not linear. All right, we're going to talk about that one in just a minute. So, but for this case, all right, there appears to be no pattern. We can assume the data, the linear model is appropriate. And that basically says, AKA, a line fits the data. And those are our two assumptions, all right? The linear model is appropriate and the residuals are normal. If those are both met, then all regression is appropriate to be conducted. Now, notice that we did this at the end. Typically, when you first conduct regression, you want to give these a quick scan before you go interpreting a million things. Looking at an example. So it seems like, and this emphasizes that residual versus X value plot. It seems like that's always seems to be a no-brainer. The problem is that sometimes it's subtle. So I want to describe, okay, so below depicts the time for a supercomputer to complete complex differential equations on an n-dimensional matrix over a 6-year span. All right, the point is that I want to describe the scatter plot, describe the association here, which means I need to identify the direction, the form, and unusual features. Okay, so the direction looks negative. All right, as for the form, does that look like a line? Yeah. And I don't see any unusual features. All right, negative, linear, no unusual features. And that is exactly how I would describe that data. Because, as I've told you many times, don't look too deeply, get the basic stuff and identify. This is why we check our assumptions. When I make my residual versus X value plot for that data, all right, for that supercomputer data. What do I see here? This is the residual versus X value plot. I want to see no pattern. Do you see a shape here?
Like this.
Starting over here. Does it do anything?
Oh, yeah.
All right. That is a parabola. Okay. So basically this says, I see a pattern here. And specifically, I see a parabolic pattern here. That means the condition fails we cannot assume the linear model is appropriate. And really, this also means check again, all right? Look back at your scatter plot and see if you missed something. So, all right, this says, look at scatter plot again. All right, so I see a pattern there when I was supposed to see no pattern. All right, I cannot assume the linear model is appropriate. I need to look here again. And really it means by saying the linear model is not appropriate, it means I was wrong there. So now I need to look a little deeper. Now, this is exactly how I would have described it, and I don't want you to overthink this. That's why we check that condition, okay? But if I'm looking a little deeper now, I think I see this. Okay, so actually it looks like it's doing that. Do we remember what form this is? This is an exponential. And now be aware, this is always, it's almost, there's no way you're going to miss a parabola in your data or a circle in your data. But what we do miss a lot is an exponential, because an exponential looks a lot like a line, right? With real data, I was like, they look really similar. Now, the good news, all right, an exponential always results in a parabola in your residual versus X value plot. So if I see a parabola in the residual versus X value plot, it means I had an exponential in my actual data. And so that's always the situation. And so that's the one we have to really, really watch out for. Okay, one last little piece for the day. So I was saying, hold on. All right, we're going to talk about what an outlier is. I said, trust me, I was saying that all last class. There are two types of outliers that need identification: leverage points and influence points. Now, only one of these, the influence point, is the troublesome type of outlier. A leverage point is just an outlier that has a very, very high X value, but still falls on the line. An influence point is exactly what it sounds like. It influences the data. And oftentimes, it determines the data in its entirety, adjusting the regression because of that point. Let's look at an example to discuss this. So, all right, there's never been any evidence relating shoe size to IQ. right? So I collected some data. I got a bunch of people's shoe sizes and I collected their IQs. And right, if I describe this, right, when I describe this data set, so direction,
So,
positive, barely, right? And I would even go so far as to say none, right? Form, none. Unusual features, none or all. So there's basically no relationship. Scattering of points, right? And that makes total sense. Shoe size and IQ, no relationship. All right, so that, okay, perfect. I'm seeing exactly what I believe to see. Now, I collected one more piece of data. Bozo the clown, very famous clown, the most famous clown. All right, he had genius level IQ. He also was a clown, so he had very, very large shoes. In fact, they were about size 25 shoes. So now if I put him in the data, notice how it's changed. All right, it took a bunch of data, but this one point took it from like kind of a little positive to very strong positive. That is what is known as an influence point. If a single or very few number of points determine the entire shape of the line, that is what is called an influence point. This is the type of outlier that needs to be A, noted, and B, studied. If I didn't know this was Bozo the clown, I would be like, what is happening? What is going on with this one point? I would look it up and I would see, oh, this is Bozo the clown. He has very large shoes and genius level IQ. So that one point is determining it. In order to identify sometimes an influence point, you can change the Y value. So if Bozo still has very, very large shoes, oh, their size actually like 26, apparently. If you then reduce his intelligence to like 50, and it totally changes the slope of the line, that guarantees that this is an influence point. So if you just, I mean, you can just physically go in and mess with that data value. And if it changes the data that strongly, I know that that is an influence point. This is also that type of point that fails our correlation condition that says no outliers. This is the one it's talking about. If you have an influence point in your data set, you fail your conditions and you stop. As a note, the other type of outlier, which is not a big deal, but should always be noted, is what's known as a leverage point. That is an outlier with just a very high X value. But now we pretend that Bozo, who still has very large shoes, just has, moderate IQ. So when I put that data value in the line, that data value in with the rest of the data, the line is still like a horizontal, basically a nothing line. That means that, that doesn't actually determine more investigating. It means that if I had people, so I only have people up to size like 12, 13 shoes, but if I filled in the rest of this data, it should ideally keep fitting the pattern. So this one should be noted, but this does not fail the no outlier condition in correlation. The no outlier condition for correlation coefficients is specifically no influence points. All right, leverage points are fine. They should be noted as an unusual feature, but it doesn't let it make us fail our conditions, because if I remove that point, nothing in the data changes. And so it's like, oh, with that point, without that point, no problem. All right, we're going to pick it up. All right, next class right here. That is absolutely everything I wanted to look at today.